Hi folks, welcome to part one of the second optimization lesson. So before we start, just a reminder that the best way to do this is for you to try these questions on your own first, see how far you can get, at least see if you can come up with a model and with an appropriate domain, and then from there, if you want to take a look at what's going on before you move on, that's great. And again, if you can't come up with a model, watch just the first part of the video and then see if you can go on your own. So best thing is to try to do some of this on your own. All right, so let's take a look at this first question here. So it says a right circular cylinder is inscribed in a sphere of radius 10, and they want us to determine the largest volume such a cylinder could possess. So right off the bat, I see that I'm working with a cylinder, and I'm looking for the largest possible volume. All right, so I have a formula that does that formula already. We have the volume of a cylinder, which is just given by the area of the base times the height. So the base is a circle, pi r squared, times the height. And right off the bat, we come across a very familiar issue, which is that we have a function given in terms of two unknowns. So we're going to have to get this to one unknown. And the constraint that they give us is that this cylinder is living inside a sphere of radius 10. Okay, so anytime you have a geometric problem, best thing to do is to work with a diagram. So let's draw, and I'm going to draw this as a cross section. So I'm going to use a circle as a representation of my sphere. Okay, and then here I have a cylinder that's inscribed inside. So I'm just going to draw the cross section of a cylinder. Will just be a rectangle. Okay, and there's my cross section. All right, so let's take a look at what we have. Well, we're working with the dimensions for a cylinder. So the important dimensions are the radius and the height as given in the equation. All right, and somehow we're going to have to bring in the radius of the sphere. Okay, now remember that the radius of a sphere is just the distance from the center to any point on the sphere. And this is where I'm going to use a trick that is very often useful when you're working with two shapes in a geometry problem, which is to find something that connects them. So let's say you're working with two triangles. You want to try to find a connection between the side length that they share. Okay, in this case here, like I said, I can draw this radius anywhere to any point on the exterior of the sphere. But what I'm going to do is I'm going to choose to draw it to a point where the sphere and the cylinder meet. Okay? And from here, hopefully you see that we will have a connection between these, because if I just bring this down and I realize that I have a right angle triangle, okay, where this is just this side length is just the radius of my cylinder. This hypotenuse is the radius of my sphere. And then this side length here is just half the height of the cylinder. All right. Now, the only thing here is I'd rather not work with a fraction if I don't have to. Okay, so I have a couple of alternatives. One alternative is, instead of working with the radius of the sphere, imagine that I work with the diameter of the sphere. Okay, I could again create a right angle triangle where one side length is the height, and then the other side length would be twice the radius. And the other option that I have, and I'm going to use this one here just so I can show you something a little different, is I'm going to use a variable to represent this side length that I've drawn here. Let's say I call that x. And what I can see is that the height is equal to 2 times x. So I've written h in terms of this new variable. And now with this right angle triangle, I can use Pythagoras to write r in terms of that new variable x, because of course I've got that r squared plus x squared is equal to 10 squared. And so I can write, and in fact I don't need to isolate r. Since I've got r squared in my equation, I just need to isolate r squared. So r squared is just equal to 100 minus x squared. Okay. So far, when we've had to rewrite an equation in terms of one variable, we've always written one unknown in terms of the other. So this is another option that you sometimes have available to you, is that you write both of the unknowns in terms of a third variable. In this case here, this x, which represents half the height. All right. So let's now take this and put it into our equation. So we can now rewrite the volume as pi times, well, r squared is 100 minus x squared, and h is just equal to 2x. Okay, and let's clean this up. Okay, so I'll keep the 2 pi, since it's just a constant, I'll keep that on the outside, since I know it won't come into play when I'm taking the derivative. And let's see what we're left with. Well, we're left with just x here, so times 100, so 100x, and then minus x times x squared, x cubed. All right, so here I have my model in terms of one variable. And the last thing I want to do is I want to determine what domain I'm going to be working on. So x definitely has to be greater than 0 because it's a measure of length. So I know that 0 has to be less than x. And let's see what the maximum value, if there is one for x here. And I see that as if I make this cylinder thinner and thinner and thinner, okay, I'm going to get a taller, thinner cylinder. This x value is going to get larger and larger and larger, but there's no way it can ever be larger than the radius of the sphere. In fact, it can't be equal to the radius of the sphere. Otherwise, I'm just going to have one vertical line, okay, which is not a cylinder. Okay, so here we've got that x has to also be less than 10. Okay, now one thing I notice about this domain is it's not a closed interval. So I can't just check these endpoints along with any critical points. I'm going to have to justify that the value that I find is hopefully an absolute maximum, because I'm looking for the largest cylinder in this interval. Okay, so just to recap here, I started off with my volume of a cylinder formula. Okay, I used a diagram to help me find a relationship to the radius of the sphere that this cylinder lives in, and I was able to write both r and h in terms of this new variable x. And then from there, I was able to write my equation in terms of one variable, and I found an appropriate domain. So now we go to step 2. We're going to apply our calculus tools to determine the optimal value. So let's take the derivative. So the derivative, okay, now I'm using prime notation, but it's implied that the derivative is with respect to the variable I'm working with, so x. So it's 2 pi is just constant. So the derivative of 100x is just 100 minus derivative of x cubed is 3x squared. All right. And of course, I want to determine when, excuse me, this is equal to 0, since the derivative always exists. So if I want to determine when the derivative is equal to 0, well, remember 2 pi is just a constant. So I just have to determine when 100 minus 3x squared is equal to 0. And so now let's solve for that. So x is going to be equal to, so bring the 100 to the other side, negative 100 over negative 3. It's just 100 over 3. And I'm taking the, of course, positive and negative square root when I take the square root of both sides. But I'm going to eliminate the negative portion since I'm living in this domain of 0 to 10. All right. Now, since they're asking me for an approximation, I'll just make my life simpler, at least for now, and find an approximation for this. Okay, I'll keep it to 2 decimal places, even though my final answer is going to be to 1 decimal place, so I don't lose too much precision. Okay, and exponent 0.5 for my square root, and I get 5.77. So we have only one critical point in our domain. But of course, because this is in the closed interval, I'm going to have to justify that this corresponds to an absolute maximum. Okay, so let's test this. So we know we're going from 0 to 10, not inclusive, and we've got 5.77. Okay, so let's test some number to the left. So let's say I pick 1, and here again, 2 pi is always positive, so 100 minus 3 times 1 squared. Well, that's definitely positive. And if I take, say, 9 on the other side, well, 9 squared is 81 times 3 is definitely larger than 100, so this is going to be negative. So essentially what we have is that 5.77 does relate to a local maximum, because my derivative is 0 and my derivative is going from positive to negative. But in this interval, it's actually going to be an absolute maximum, because from 0 to 5.77, this function is constantly increasing. And then here from 5.77 to 10, it's always decreasing. Okay, so in fact, in this interval, this corresponds to an absolute maximum. Okay, so we found the value of the variable that gives us the largest possible volume of this cylinder. So now that I've finished my calculus, let me go back to the question and see what they're looking for. And I see that what they want is the largest volume. So they're not looking for the dimensions. If they were, I would just take my x value and stick it into my h, stick it into my R squared equations and calculate those, but they're actually looking for the volumes themselves. All right, so I'm going to use this equation here in terms of x, okay, to determine my answer. So let's see what we have here. We have that my answer is that the volume is going to be given by 2 pi times 100 times 5.77 minus 5.77 cubed. All right, so let's get our trusty calculator here. So what do we have? We have 100 times 5.7, oops, sorry, 100 times 5.77, and then minus 5.77 cubed, okay, and then multiplied by 2 and by pi, and we end up with 2418.4. So 2418.4. All right, and here, since the dimensions were given in centimeters, this is just going to be centimeters cubed. All right, so again, let's do another quick recap here. Step 1, equation in terms of 2 variables. Use the constraint that's given with a good diagram to help us write this in terms of 1 variable, found an appropriate domain, applied my calculus tools, justified that it did relate to an absolute maximum on my domain, and then from there I answered the question that was posed. All right, that's it for this one.